Hello class, and today we are talking about line integrals. So the music recommendation for lecture today is the album Color Theory by the artist Soccer Mommy. And I want to especially point out this excellent album. The whole album is fantastic. Listen to it straight through, but if you're the type of person who only wants to listen to one song, go listen to Circle the Drain. It is just really good. Singer-songwriter, indie rock, just beautiful. I liked Soccer Mommy's last album. Just really excellent artist putting out amazing music. This is from earlier this year. So, today we talk about line integrals. So, the input to everything we do today is a field, by which I mean a vector field, f, and a path, which is going to be a vector valued function, and the output is a number, which is going to be the integral over the path c, where p is parametrizing c, and the integral over c of f dot dp. And this is going to be a number, i.e. a scalar, that we associate to this field and this path. And so how do we make sense of what it's doing? Well, let's draw a vector field. Okay, here's a vector field. So here's f. I've drawn a bunch of vectors down to look at what f is doing. And now I'm going to draw a path p. And let's draw that in a different color. Ta-da! There it is. So the blue curve is the curve c. And so it's a curve that starts and stops at different points. And so if you have picked a parameterization, let's say p is mapping from the closed interval 0, 1 to c. So p of 0 is over here, and this right here is p of 1, and all of the points in between are, different values. So maybe this corner point here is p of 1/2, and right here is p of 1/4, or something like that, right? But someone has produced a parameterization of this path to walk along it. So what is the output that we associate to this path and this field? It's supposed to be a number, and it's sort of supposed to tell you how much you are moving with the field. So how much p agrees with f. So over in my example, I kind of made p out of two distinct curves, one of which, this first half, is kind of closely following c, so that's the part in blue, but now I'm going to change the second half and make it green. And so that green part of the curve seems to be moving across the flow. So if you imagine this as a current in a stream, then if your blue path might be the sort of path that a bottle could take if you just threw it in the water. But then, in order for the bottle to move along the green path, you have to have, a propeller on the bottle that's moving it across the stream. It has to be under some propulsion. It's working against this flow of the stream, so it's kind of working against the field. Okay, and the reason the reason that this is the correct way of interpreting what this output is because there is a dot product here. And so the dot product is supposed to tell us how much the vector given by f at a point is agreeing with the vector having to do with the derivative of p at the point. And we've already said that the derivative of a path is kind of like a tangent vector. So if you think back to when we were talking about parameterized curves, if we have this function p of t, it might be given by, as a vector value function, as x of t, comma y of t. Then if we take p prime, it would be like taking derivatives with respect to p at each time. So that would look like x prime of t, y prime of t. And this would give you a tangent vector to the curve. At the appropriate time. So another way to say that is that dp dt evaluated at, let's say, t equals a would be tangent to p at time a for some time a, right? Now, in order to make sense of this expression, what I'm going to do is actually fix this notation here for p, and I'm also going to fix notation for f. So I'm going to write f, which we said was a function of x and y. Well, it's vector valued, so it has to have two components because it's from R2 to R2. And I'm going to call the first one m of xy, and the second one n of x comma y. Okay, so let's now make sense of this expression in general. And so in general, I'm going to assume p is mapping from a comma b to c to our curve c. So that p of a is the starting point, and p of b is the stopping point, is the end point of the curve. Okay, let's scroll down and take a look at this. So now we're going to just do some sensible definitions. So we already know what f is, and I'm just also going to tell you what dp is. And you could probably guess what dp is from this boxed expression. But we have to kind of get rid of the dt's everywhere. So dp is going to look like just dx comma dy. Okay? And f is m comma n. So the integral that we care about, the integral over c of f dot dp, that's a dot product of two things which are vectors. So let's take the dot product. So that's the integral of m comma n dot dx comma dy. That looks like the integral over c of m dx plus the integral over c of n dy. And we could get rid of this second integral. Maybe that's just confusing. And just treat this as one big integral. All right, so that's my dot product formula. Now the thing is, this integral is happening over c, and so we only actually care about using like we have a way to parameterize C. So we're going to parameterize C using P of T. And so what I want to do is plug in P of T into this expression. So this is going to be a little chain rule thing. So what that means is, let's scroll a little bit more. What I'll do is I'm going to switch to my time coordinates. So my time starts and stops at A and B. And then where am I at M at this left-hand component, right? It becomes M of P of T, wherever I am at that given time, dot, or times, dx. And dx is now going to be dx dt dt. Okay? And this is really just chain rule. So what I've done is I've plugged in P of T, and I'm adding this little thing that looks like P prime of T. Except, well, P prime of T had a vector, so this is just like one of the components of it. And that happens because we split it up. So let's see the other component as well. So this component over here is going to become, after plugging in P, N, let's write it in black, N of P of T, and the dy becomes a dy dt dt by chain rule. And now both of these parts are part of P prime, the vector P prime, right, which we wrote up here. And so sometimes people like to rewrite this whole integral in maybe an easier way to remember, because dot products are straightforward, is rewrite this as the integral from t equals a to t equals b of m and n are just f. Both of them I'm evaluating at P of T. And I'm taking a dot product with P prime of T dt. And so just to be super clear, this is, so this full green underline is these two components, and this guy here plus n there is this guy, and if you dot product them out, all I'm doing is kind of unexpanding my dot product. So those are the kind of ways to look at what this formula is telling you. So sometimes people like to suppress the p coordinate, and so maybe you could rewrite this as t equals a to b of m dx dt plus n dy dt dt, and it's just understood that m at time t is m of p of t. I don't know, sometimes this is convenient. It kind of depends on how m and n are presented to you. But hopefully this makes sense how I can manipulate these sorts of expressions. Really, I'm just using the dot product and chain rule to parameterize my curve. Let's look at some examples. Before we look at examples, actually, we should look back up at our example that we drew and try to understand what this means. So let's give ourselves a little bit of room. So So let's look at this little picture that we drew. So I'll scroll up. So if you imagine yourself kind of walking along, integrals add up lots of numbers. So the numbers you're adding up are the dot products of your path and its tangent derivative. So that's my p prime at time t. And maybe f. So here it looks like here's what f is at p of t. And so you can see that those two angles, or the angle between those two vectors is pretty small. So what you're getting at that point is essentially, it's the dot product of those two vectors, but since the angle between them is small, or, at some later points, it's very close to agreeing. It looks like they're actually flowing exactly along each other. Then the dot product is maximized, and so you're getting a very high number that you're adding up, or as close as you can to just multiplying these two things times each other. Now, if you're on the green curve, then f at time t is going up, but your tangent direction is orthogonal to that, and so you're going to get you're going to be adding 0 to your integral. So you're just taking a big integral that adds up at a bunch of different times, 0, 0, 0, 0, 0. So in this example, what I'm going to write is that the integral over c of f dot dp is basically equal to the blue part of the integral just from p from time 0 to 1/2 of f of p of t dot dp, so that's p prime of t dt. And we know that there's plus this other integral from time 1/2 to 1 of f dot dp, right? Maybe I should write that out more carefully. Of the same, right? F of p of t dot p prime of t dt. But this analysis tells us all of this goes to 0. And so the only part that is contributing anything is this first blue part, where we're closer to flowing with, or sort of agreeing with, the flow of the field. And when we're moving orthogonal to the field, we do not pick up any additional component of our line integral. So that's line integrals. Let's look at examples. So our slogan for line integrals is that the line integral, the integral over c of f dot dp, measures the flow of f along c, parameterized by p. So our first example, we will consider the radial vector field x, y for f, and we'll let c be a quarter circle. Going through the first quadrant. So let me draw that. So here is my drawing of this picture. So I've drawn f in blue, and I drew c in green. You always need to pick an orientation of c, of the curve. So I need to tell you, am I going it from, the x-axis to the y-axis, or the y-axis to the x-axis? So I'm going to indicate that with just this little arrow to tell me I'm doing c in that direction. If you were given a parameterization of c, then, some formula for p, whichever way p is flowing would tell you the orientation on c. So I'm going to let, for us, p be, well, whatever the radius of c is. So let's say c has radius 2, let's say. Let p be 2 cosine t, 2 sine t. From our section on vector valued functions, this is a circle parameterization. And so in order to get just the quarter circle, what I need to do is allow t to go between 0 and pi over 2. And that's going to be my path. So let's now first figure out what we expect to be true, and then double check that it is true. So at every point of C, my tangent vector and my radial vector are orthogonal to each other. So my expectation is that this integral should be 0. So I'm expecting that C is entirely moving against, perpendicular to the flow. So the integral along C of f dot dp should equal 0. And now let's just double check that. So the integral along C of f, so f was x comma y dot dp, so dx dy. We said using the parameterization of p, so p, this is x of t, y of t. So this becomes the integral as t goes from 0 to pi over 2 of the y coordinate of p. So let me color this as I'm filling it in. So my x value is 2 cosine t. My y value is this 2 sine t. So that's now what f looks like when I'm plugging in p for x and y. So let's just write this. This is f of p of t. And then I know I need to do a dot with p prime of t dt, and that's going to fill in for my dy dx, or dx dy. So this guy is this after we switch to parameterizations. And so what does that become? P prime looks like minus 2 sine t to cosine t dt. So my integral, if I do this little dot product, I get integral t goes from 0 to 2 to pi over 2 of negative 4 cosine t sine t, and then plus 4 sine t cosine t dt, and that all cancels, so I just get 0. And it's canceling just because this adds up to 0 in the integrand. So hopefully this makes clear kind of how this heuristic works. Let's also compute the flow along a different path, one that's not a quarter, not a piece of a circle, so it's not entirely orthogonal to the path. So let's make this new path. I'm going to scroll down and copy this. Okay, so our new curve is going to be this red radial curve. I'm calling it C2. So if we're going to parameterize that, we said that this over here is distance 2. C1 had radius 2. So for C2, our parameterization, let's call this P2 for C2. P2 is a time of t, is going to be, well, I have to pick some angle that I'm going at, so why don't we make that be the vector 1, 1, That's not a unit vector, so if we make it a unit vector, we divide by its length, root 2. And so then if we want to go out to time 2, we could just multiply this by t. And so t is now varying between 0 and 2. And t also represents how far you are from the origin. So t is kind of counting the distance away from the origin that you are on this line, on this radial line. So, great. So if I were to write this out in xy coordinates, this looks like 1 over root 2 times t, 1 over root 2 times t. So my integral over c2 of f dot dp is, let's do this a different way. This is time t equals 0 to t equals 2 of f of, I should write p2 of t dot p prime of t, p2 prime, dt, and I put a dot there, but it's just ordinary multiplication, so just dt. And now each of these I can fill in on their own. So recall f was x comma y, which means f of p of t looks like 1 over root 2 times, and this is scalar multiplication, t in each coordinate. That's just another way of writing p2 of t, right? It's scalar multiplication times tt, 1 over root 2 times tt. So this is going from t equals 0 to t equals 2. It's t comma t dot p prime, which is 1 over root 2, 1 over root 2 dt. You might notice that this is really the same as 1 over root 2 times scalar multiplied by the vector 1, 1. So I can pull both of the scalar multiplications out in front and multiply them together. That looks like 1 over root 2 times 1 over root 2. That's a 1/2. The integral from t equals 0 to t equals 2 of t comma t dot 1 comma 1 dt. So if I add that up, or expand my dot product, that's t times 1 plus t times 1. That's 2t dt, t equals 0 to t equals 2. And so this just cancels and gives me the integral of t. That gives me a t squared with a half, evaluated from t equals 0 to t equals 2. And my final answer is 2 minus 0. So what we can observe from this example is when we're on a path that's flowing with the field, so when I'm moving along this reg path in the direction of the field, I'm getting this positive output telling me how much my field is flowing along this path. Meanwhile, in C1, I was kind of moving entirely perpendicular to the way the field was moving out, and that's why I got 0, because the field didn't flow along the green curve at all. It flowed 0 along the green curve. And if you take more complicated paths, like maybe a curve like this, or some semicircle, pick 2 points and pick some squiggly path between them, these integrals just get harder depending on how hard it is to parameterize p and what the integral ends up computing to look like. So it depends on kind of how hard f is and how hard your parameterization is for p. I will remind you the things you should definitely be able to parameterize are circles or lines. And moving forward, we'll also see planes come back, but these are the big ones, the circles and lines, believe it or not. Yeah. Okay, for the next example, our function f is going to be 0 comma 1, our vector field, f is 0, 1. So it's just constantly flowing up. These types of constant fields actually happen in lots of modeling examples in nature. So like if you are in a really strong electromagnetic field, it could look like this, basically constant and uniform across some area that you're doing something in, like taking a like a CAT scan of someone's body. So, or sorry, an MRI scan of someone's body. So, how do we make sense of different vector field flows along different curves? So let's just like look at 3 examples and try to eyeball what we think is going to happen. And so for each of these, the question is going to be, is the integral along C of f dot dp positive, negative, or 0? That's a question. So for the first one, we'll take this red C1. My flow is going to be just, my path that I'm taking is going to be from here over to here. So here's the direction I'm flowing, and here's my endpoint, and here's C1. For C2, I'm going to go from this point here to this point here along a straight line. So here's C2. And then for C3, I'm going to kind of go the other way. Let's go like this. This will be, let's go like this, endpoint, starting point, C3. So take a quick stab, try to figure out what's going on. And now that you're back with me, 20 milliseconds later, let's analyze these. So in C1, so I'm going to draw my vector field f with black coordinates. So dp, like the tangent derivative at one of these curves at any point on C1 is pointing to the right, and f's pointing straight up, and those are orthogonal. So this integral is a big integral of zeros for all of time, which means you get 0. So the red one should be 0. For the blue one, you're moving this way, down right, and f is moving up, and that angle is obtuse. It's bigger than 90 degrees. So the dot product should be negative. So when you add up a bunch of negative numbers, and it's the same negative number, right? It's the same negative number up here. And the only way that you could change what the number is by changing the speed that you're going on C2, which would change the magnitude of the blue vector. But it's still going to be negative. So as long as you're flowing continuously along C2, you're going to get a negative number. So this is negative. And for C3, the story is the opposite, that C3, the tangent vector to C3 and f are forming an acute angle, so you expect the dot product to always be positive. And again, like it might be that at some points in C3 that speed is slow in your parameterization. You don't have to walk it at a constant speed, but f looks like this. So maybe f dot dp at this point is kind of small, but it's positive. Meanwhile, if C3 is going really fast, so speed, we still have the same angle, but maybe the green vector is much longer than f, then you expect the dot product to be bigger, but still it's large, but it's positive. So hopefully that gives you a eyeball of what's going on in these types of pictures. Yeah, and I should point out that f in this case is a gradient field, so yeah, kind of in the back of our head, even in all these examples, you should still be thinking, is the thing we're doing a gradient field or not? So yeah. Let's take one more example with the same field, and it's going to be kind of an oddball. So I'm going to take the same starting points as C1, but I'm going to do a little parabola. And so here, this is C4. And the weird thing about C4 is part of it, you're going, you know, over here, your tangent is down and it's up, and so it looks like you should be getting negatives, right? So it's like negative flow for the first half. And then for the second half, it looks like positive flow. And I should mention, like, sometimes people like to imagine these flows as just if you were living on this parabola, and you're sure that the traffic flow on the parabola is from the left endpoint to the right endpoint, then if you were at one of these points and you projected f onto the tangent plane, so you did a little projection. Here's what f would look like, kind of projected. F is moving backwards against the flow, which is why it has negative flow against the way traffic is moving along your parameterization. And so in this case, what you'd actually expect is that if you divide this parabola in half, on the first half, it should be giving you a bunch of negative flow. And on the second half, it should be giving you positive flow. And those two things should cancel out. So here, you expect the integral over C4 of f dp to equal 0 because the negative half and positive half cancels. So because of cancellation. And that's a little subtle, and we will develop better tools to analyze this moving forward. Okay, so our next problem will be to use 3 different parameterizations of C, and C here is going to be the unit circle oriented counterclockwise. And what I want you to do with each of those parameterizations is compute the line integral of f dp along C, if f is this vector field that we've seen before, minus yx. Now, minus yx is the rotational vector field that moves counterclockwise. So if I draw C in green, the C looks something like this. So let's draw a better circle. That's okay. Here's C. It's the unit circle, 1, right? And F, F was moving rotationally and counterclockwise. So F looks to kind of like that at that point, kind of like this at this point, kind of like this at this point, kind of like this, kind of like this, like that, like that, and like that. And it got more swirly as you moved out, right? So what I want you to do is compute this. Our expectation should be that this is positive because we are flowing along C counterclockwise, and at every point, F and the tangent direction for C both agree. So F is pointing in the positive, tangent vector direction for C. Both of them are going counterclockwise, is what I mean. The final note I want to point out is people use this notation for an integral, for a line integral, with a little circle in the integral sign for when the integral is happening over a closed curve. So in this particular case, so this is the line integral over a closed curve. And what that means is that P starts and stops at the same point. So open curves, or not closed curves, would be some path going between two different points, but closed curves are paths that start somewhere and then come back to where they stop. So for a closed curve, P of A, if A is where you start, and P of B do not have to equal each other. But over here, P at time A and P at time B have to be the same point. So because, so sometimes people call closed curves loops, although they can also be a little bit more complicated than loops, so sometimes that is reserved for a different definition, but you can think of them as loops. And this integral notation with a circle in it is to remind you that you're doing an integral over a loop, and we're going to see increasingly that that matters. So write down 3 different parameterizations and try computing what you got. So here are my 3 picks for parameterizations. So in the first one, I'm picking cosine t sine t. This is like our standard parameterization of the unit circle. It starts at the point on the x-axis and goes around counterclockwise once if I go between 0 and 2 pi. For my second parameterization, I picked the same function, but I'm changing my start and stop points. So now I'm starting up here at pi over 2, I'm going around counterclockwise, and I'm stopping at pi over 2. So those start and stop at different points. And for P3, so that makes it a different parameterization because they are really doing a different path, right? And P3 starts at over here and does this loop and stops here, but it does it twice as fast. So it does it during time 0 to pi because it just zooms. And so at pi over 2, you're already here, and then back here you're at pi. So those are my 3 parameterizations. And if you didn't come up with 3 parameterizations, try pausing now and work out what those line integrals are. So for the first one, if I plug into f, my minus y terms becomes minus sine t. My x term becomes cosine t. And here's my derivative of p1, so it's minus sine t cosine t. If you take this dot product, you'll get sine squared plus cosine squared, so that's just 1. So I'm integrating 1 dt from 0 to 2 pi, which is nice and easy. I just get 2 pi, because that's the length of the interval. So for the second one, my parameterization function is the same, so my integral looks basically the same, and the only new feature is my bounds change. And so when I integrate and I get a t, I evaluate, and the difference between these is still 2 pi. So for 1 and 2, I got the same answer. For problem 3, though, we're going to get things a little bit differently. So when I plug in for p of t, I go from 0 to pi for my bounds on t. F becomes minus sine of 2t, cosine of 2t, dot, and my derivative, oh, now there's a chain rule term, so I'm going to pick up a 2 for each of these. So 2 times minus sine of t, minus sine of 2t, 2 cosine of 2t, dt. And I can pull those 2's out, and then what I'm left with is sine of 2t squared plus cosine of 2t squared. So my integral becomes 0 to pi 2 times 1 from the sine squared plus cosine squared dt, which also gives you 2 times pi minus 0, which is 2 pi. So the thing to say here is that path integrals are in fact independent of the parameterization you pick. So it didn't matter whether we used 1, 2, or 3, we always got the same answer. And when you make the path go faster, or if it's a closed curve, start and stop at a different point, all you're really doing is changing maybe some bounds, or you're adding a derivative term, but it has to cancel something, right? So like, if you go faster through your path, then your time interval is shorter. And so then this extra amount of contribution from the derivative cancels out that difference. So it turns out that line integrals are always path independent, which is why this kind of way of writing them, I don't really have to specify what P is. I do have to specify what C is. And I'll mention this again in our summarization at the end of the lecture. Okay, let's talk about the fundamental theorem of calculus and the fundamental theorem of line integrals. And this is the first big giant tool that we get to have. And you should think about this as the fundamental theorem of calculus plus. It's our first improvement for the fundamental theorem of calculus. And we're going to give better and better versions of the fundamental theorem of calculus moving forward. Or perhaps I should say new versions of the fundamental theorem of calculus in a bunch of different settings. So the fundamental theorem of calculus, as you know, says that if I'm computing an integral of f prime of t dt, so if I'm taking the integral of a derivative from a to b, I can take the antiderivative, so the function that I know this is the derivative of, and just evaluate. And the way we will think about this in this class is if you imagine having a parameterization of the unit interval, so maybe it is kind of suppressed, but we're using a parameterization of t, which is just the scalar number t, right? So this is like a one-dimensional parameterization. So we're plugging in, t into this function, and we're starting and stopping at a. The version for line integrals is now we're allowing our paths to be wiggly, so rather than staying on the x-axis, they can kind of move all over in the plane or in three-dimensional space. And the new formula says that if I'm integrating a gradient field, which we already know we have a way to detect whether a field is a gradient field, then what I can do is just construct a potential function, which is our version of an antiderivative in multiple variables for a gradient field, and evaluate the difference between f at the endpoints to get the value of the total flow over the curve. So this is telling you that the flow over the curve, of a gradient field only depends on the endpoints. And it doesn't depend on the field at the endpoints, it depends on the potential function at the endpoints. And this is super useful. So let's look at an example. Okay, so here's a curve. It's a squiggly curve in the xy plane. It's a closed curve, and so what I want to compute is the flow along this closed curve of the field f, which is y cosine xy, comma x cosine xy. And I don't have any way to parameterize c. I didn't even really tell you enough to give a parameterization or any coordinates for it. So you you're kind of out of luck to try to solve the problem that way. But what you can notice is you can try using the Clairaut test for f. And so if I compute f, let's just give these guys names. Let's call this m, this n. Then nx is minus my, so this is our scalar curl. Looks like the derivative of x cosine xy is cosine xy plus x times derivative of cosine, which is minus sine. So let's just go minus x sine xy times the chain rule term y, and minus what I get from the derivative of m with respect to y. Well, there's a lot of symmetry between these, so when I take the derivative with respect to y and I do a product rule, the first one is cosine x y, and then when I take the other half of the product rule, I do plus, derivative of cosine is minus sine, so it'll be minus y times sine of xy times my chain rule term, which is x, and you realize, oh, that's, if I just move these guys back and forth, that everything above cancels, so all of this is 0. And so by the Clairaut test, f is a gradient field. In fact, f is the gradient, you can sort this out, of the function sine of xy, which isn't super surprising, because I see this cosines showing up in both cases. And so my line integral along this closed curve is equal to, well, if I call this point where I'm starting, just let's p, since it's closed, p of a equals p of b, and so what I'm doing is evaluating this new function, sine of xy. Sine xy may be evaluated at p of b minus sine xy evaluated at p of a. Oh, but those are the same points, so whatever is at that point, it's the same at both of them because they're the same point, so this is always just 0. So this brings us to kind of 3 definitions for vector fields. So the first one we already know. So if G is a vector field, then we say it's a gradient field if G is equal to the gradient of f for some potential function f, right? We will say that it's path independent if the integral or the flow of G along a curve C depends only on its endpoints. So if this is independent, or let's say is equal, for any curve C from the endpoints, let's say with the same endpoints. And so my picture for that is if C might look like this, but C could also look like this. Notice, though, that which endpoint is the first endpoint. So maybe this is C prime, this is C double prime, like several options for C. The orientation of C is fixed, so C triple prime. So the orientation is fixed. So same orientation. So like whichever endpoint is a and whichever endpoint is b, those are the same for these different integrals. And finally, the third definition is a conservative, G is a conservative field if the integral over any closed curve, G, dp, is 0 for any closed curve, C. And so now that means C could look like this with those points, but C could also be like this totally unrelated curve over here. And maybe it goes counterclockwise rather than clockwise, so C prime, etc. So any closed curve you draw in the plane. And the corollary of the fundamental theorem of calculus is that all these three definitions are the same. So let's just write that down. So corollary of the fundamental theorem of calculus for line integrals is G is a gradient field if and only if it's path independent if and only if it's conservative. So why does this make sense? So we've kind of already seen that the first two imply each other from the fundamental theorem of calculus directly. So if it's gradient, then I can use the fundamental theorem of calculus to tell me that the integral of G along, if G is gradient, then G is the potential for f. So the integral of the potential of f dp, well, that only depends on f at the different endpoints. So it's f of whatever p of b is minus f of p of a, and it has nothing to do with c is. So even if I switch c but keep the same endpoints, I'm going to get the same answer. And then conservative is telling me about closed curves, and that's when p of a and p of b coincide. And so the fundamental theorem of calculus tells me that I always get 0. And so this is a very useful sort of different set of ways to interpret the fundamental theorem of calculus. So rather than going back to it every single time, if you look at a closed curve, like in our last example, and you say, oh, it's closed and the vector field is a gradient field, therefore the integral is 0 of the flow along C, that's good. That's just a great argument right there. Very powerful tool, fundamental theorem of calculus. So I also want to include this theorem because we didn't prove it, and I sort of buried it in an example, but the integral of any path integral, so the integral of any vector field dp does not depend on your choice of parameterization. P for C. So if you and your friend both compute different parameterizations of a curve, provided they have the same orientation, then you are going to get the same value for a line integral. So the line integral really only depends on what the curve is, not how you are choosing to move along the curve, except for the way you have decided where the curve starts and where the curve stops. So like, are you flowing counterclockwise or clockwise or left to right or right to left? That matters, but it doesn't matter how you particularly write down that parameterization, which will save our butts in a lot of these problems. For example 5, let C be the curve indicated, this squiggly S-shaped curve, from A to B, and I want to compute the integral over C of minus y dx minus x dy. So take a stab at that and check in. What is essential in these problems is to reinterpret this as a path integral. So this way of writing it in terms of x's and y's, which happens all the time, doesn't look the same as our vector valued way of writing it. So what I need to do is unpack this into by undoing the dot product into something that looks closer to my examples. So this looks like minus y comma minus x dot dx dy over integral c. And dx dy, that's dp that we're writing down. So minus y minus x, this is going to be my vector field f minus y minus x. Now, if I let f equal minus y minus x, the first thing we could try doing is seeing, is f a gradient field? Because if it is, it would be path independent, and then we could pick a different path than c to compute this over. That is our goal. So what I would do is say, okay, so what's the scalar curl? Be the derivative of minus x with respect to x, that's minus 1, minus derivative of minus y with respect to y, which is minus 1. So 1 minus minus 1 is 0. So f is gradient. So what I can do is use the fundamental theorem of line integrals. So let's find a function for which f is the gradient. So my potential function, which I'm going to let be p of x, y. In order to have its xth derivative be minus y, it kind of looks like it has to be minus yx, maybe plus a constant. So I'm just getting that by analyzing what's happening on this first coordinate. So for that to be my fx coordinate, I kind of have to have something like this, plus a constant with respect to x. So that's constant with respect to x. So there could be y's in there in the c, and then, but then you go back and check and you say, okay, if I take f dy of this, I get minus x, and that plus whatever the derivative of the constant is, but I wanted to get minus x. So I'm already good. So I'm going to just let this be 0 and let this be my potential function. And it does, just by checking out, gradient of p equals f. So I'm already kind of set up, right? And so now the only remaining point is to find the values for a and b. So a looks like the point 1, 2, and b looks to me like the point 7, 6. So my conclusion is that this is equal to minus yx evaluated from where x, y is my starting point, so 1, 2, up to where x, y is 7, 6. So my answer is that the integral of c over f dot dp, as given, looks like minus 7 times 6 is 42, so minus 42, minus 1 times 2, so 2. So minus 42 plus 2 is minus 40, and I'm done. Okay, and our final example of today, let's look at these two little graphical expressions of vector fields, and the question is, are either of these gradient fields just from looking at the picture. So the critical thing is it's hard to eyeball if something's gradient, like what is a potential function, is this a gradient field? But the other two interpretations are easier to check. So it's easier to check, is it conservative, which means that closed curves have integrals have zero flow, always, or is it path independent? Which I don't think I mentioned this before, but how do you go between path independent and conservative? Well, if you know something is path independent, so it only depends on these two endpoints for any pair of endpoints, you take one curve going this way and another curve going this way, and so C1, C2. So if the integral over C1 of f dot dp equals the integral over C2 of f dot dp, then integral over C1 f dot dp minus the integral over C2 f dot dp is 0. But doing the integral over C1 minus the integral over C2, this is the same as doing the integral backwards. So this is the same as doing C2 backwards plus C2 backwards. So minus C2 is this blue curve. So it's flowing in the opposite direction of C2. And if you look, doing C1 and then doing C2 is starting at this point, doing C1 and then doing C2, and so you're doing a loop. And so, you can translate any question about a loop into, split the loop into two pieces, and because of path independence, each of those pieces have to add up to the same amount, but then you turn one around, and you get this sort of cancellation property. Okay, that's kind of an aside. So what matters for this problem is it's easier to eyeball conservative or path independence. So let's draw some paths, and then that tell us that these things can or can't be gradient. So, for instance, this left one, I can take a path where I start at this point, and I travel up. I'm going with the flow, right? Then let's stop at some point and sail entirely perpendicular to the flow. And we already know that this part here will give us positive flow. This part here is going to give us zero flow because we're moving perpendicular to the direction of flow. Then at this point, we're moving with the flow again if we go south, so that will give us more positive flow. And then we can turn and sail back, and we get zero flow on those sideways moves. So at least with this picture for this flow, it looks like I can take a path where I go entirely with the flow or perpendicular to the flow. So I'm going positive flow or zero flow, but when I add up all the little pieces, I end up getting a total closed curve whose integral along it, whose flow along it, is non-zero. So this is not conservative. So one way people sometimes think about this is a gradient field needs to look like it's the derivatives of something. So if your derivatives are telling you how you're changing height, then if you can walk entirely around back to where you started on a path like this, and you end up higher than where you started, then it couldn't have been the graph of a function. So you're doing a closed curve and you end up taller than you started. Yeah. So over here on the right, though, it looks to me like if I take any sort of path, this needs to be I'm canceling stuff. So even if I go with the flow and then perpendicular to it, then this portion here is canceling, it's negative flow. And the positive flow and negative flow in those two pieces, well, they're totally symmetric, so they're going to cancel. And so then, and that would give me zero flow. So it looks like I should be canceling things positive and negatively. And in fact, each little strip of this is the height function. So you should think about this as cross-sectionally. This looks like some function that is like this. So the derivative kind of moving away. I should draw it the other way, sorry. So what I mean to say is that at this point here, we have zero derivative. So like the derivative in the x direction is zero. And in the y direction, we never have any derivative. So this function has kind of the same cross sections like this everywhere. In fact, it looks kind of like a parabolic cylinder. So it looks something like that. So it's got cross sections, parabolas, and they're downward facing. And as you move out from it, you're getting bigger and bigger negative x slopes because you're falling down the side of these parabolas. So this does look like the gradient field, and it looks like the gradient field maybe for the gradient of something like minus x squared. And so you could go try graphing this gradient field, and you're going to get something kind of like this. But first checking with, hey, if I draw any path, are things canceling or are they not canceling is a good way to tell you whether what you're getting is a gradient field or whether it's just not. That ends today's lecture.